Welcome everybody to lecture number 5, which is about waveguides. It will be the first lecture regarding the waveguide. What is the meaning of waveguide? Like traditionally speaking, we can say that a waveguide is a hollow conductive metal pipe or tube that can carry high frequency radio waves. But in more general terms, a waveguide is a structure to guide electromagnetic waves like radio wave and microwave. And there is like an overlap between transmission line and waveguides. Both of them are used to direct electromagnetic waves. Also, there is some overlap, some structures like the coaxial cable can be called coaxial transmission line or coaxial waveguide, because it can be dealt with as both structure. Here I'm showing a number of famous waveguides, the rectangular waveguide, circular waveguides, elliptical waveguides, and those rigid, single and double, like single rigid waveguide and double rigid waveguide. All of those does have their own applications, but the most famous I had dealt with is the rectangular waveguide. Waveguides does have the advantage when it's compared to transmission line. As I said, both structures are used to guide electromagnetic waves, but the waveguide does have like two main advantages. Number one, it's low loss. Number two, it's more immune against interference and noise because it's a closed structure mostly. While transmission line is generally much cheaper, less size and weight. The waveguides in general is bulky and expensive, especially when we go at lower frequency, because as we know that the dimensions of the waveguide is inversely proportional to its operating frequency. So for example, the coaxial line is shielded, but it has the problem that it's a difficult medium to fabricate complex microwave component. There is another category of guiding structures, which are the printed circuit board transmission line, like the strip line, microstrip, coplanar waveguides, that also used to guide electromagnetic waves. And those BCB transmission lines or waveguides or whatever guiding structures does have like many advantages compared to the other. Like they are cheap, they are very easy to integrate with different components like power amplifier, transistor, and so on and so forth. But again, its power capability is limited, so it can't carry high power. So different guiding structures, different electromagnetic wave guiding structures does have their own advantages and disadvantages. So the usage like change from application to application based on those like properties or features. So now we're going to start our analysis for the waveguide. Let me just adjust this. Okay, so let us start our analysis for the electromagnetic waves that exist in waveguides. So we'll start our analysis by, let me bring the pointer. Okay, here to go. Okay, so we'll start by finding the general solution of Maxwell's equation for different modes of wave propagation inside waveguides. Those modes are transverse electromagnetic, transverse electric, and transverse magnetic. We'll talk about the different feature of each one of them very shortly. So the general structure that we're going to use is this cylindrical structure cylindrical structure but of arbitrary cross section. So the cross section doesn't need to be like a regular shape or like a circle or whatever. It can be any shape. So cylinder means that along one direction everything is uniform, and this direction that we choose to have like uniform across is the z-axis. So we assume this kind of cross section is extending along the z-axis in both sides to infinity with some internal conductor or without internal conductor. So our analysis theoretically first will be like handling both cases. So the case of hollow structure like circular waveguide of this category, rectangular waveguide, or with some internal conductor like coaxial cable, which is of this category. So those structures are uniform along the z-axis. So those structures, as I said, is assumed to be uniform in the z direction. The conductors, which is the boundary for this hollow pipe, or like the conductor used for the inner conductor and our like conductors, are assumed to be perfect conductor first, so that we can like simplify our analysis. Later on we can add losses similar to what we did with the transmission line. So we are starting by like assuming or like writing down the expression for the field. We'll assume like it's a time harmonic with e to the j omega t dependency that we covered in like previous courses in undergraduate when we talked about Maxwell's equation, and also we reviewed this in the first lecture. So this will be like an implicit term that we don't write, but we know it does exist. So the 3D or the spatial expression of the electric field and magnetic field will be written in this way. Like E of x, y is the transverse component of the electric field. Ez is the longitudinal component, because we are assuming the waveguide is extending along the z-axis, so the wave is either propagating in the positive z direction or in the negative z direction. We will solve or do the analysis for a wave propagating in the positive z direction, which does have this expression e to the minus j beta z. And if we wanted to like solve for the wave propagating in the negative z direction, all what we need to do is to make this plus. Similarly, for the magnetic field, we'll like just write it in two component: transverse component, which is the component that is like aligned in the or parallel to the xy plane, and a longitudinal component, which is a component propagating along the z-axis. Both of them, like the transverse component and longitudinal component, does depends on x and y. The dependency on z does have this expression depending on the direction of propagation. As I said, we are assuming at the beginning a perfect conductor and a perfect dielectric, so there is no losses. That's why the propagation constant is pure imaginary. If we have losses, the losses should be small, and all what we need to do is to replace j beta with alpha plus g beta, similar to what we did in the transmission line previous lecture, and which is called like a perturbation technique. So this is our starting point, the expression of E and H, the time harmonic, and just considering wave propagating in the positive z direction, the wave propagating in the negative z direction can be obtained the same way. All what we need to do is to change this sign. So the waveguide where we do the analysis is away from the source, so it is a source free region that where we do our analysis, and our guiding or our governing expressions or law for waveguide analysis is Maxwell's equation. Maxwell's equation, when we are in a like source free region, does have this expression. We have e to the minus j beta z dependency, and we have e to the j omega t time dependency. So just substituting here, j omega t has been substituted here. This is the time dependency. And if we just write down like the curve for x, y, z, like Cartesian coordinate system, Maxwell's equation, each equation will produce three equations: equation in x, equation in y, equation in z. For h, same thing for e, we'll have like three different equations. These two Maxwell's equations will be expanded into 6 different equations as shown here. So those equations can be reduced to these 4 equations. All what we need to do is that this is Ez, so we'll take this equation and substitute it here. We take also this Hz equation, substituted here. So we'll have 4 different equations. So those 6 equations by substitution can be reduced to 4, as we are seeing here. So we just like the equations had been like reduced to 4 equations: hx, hy, ex, ey. Both of them, like all of them, depends on Ez, Hz. So we wrote the transverse component of magnetic and electric field in terms of longitudinal components of electric and magnetic fields. In these equations, Kc equal k square minus beta square. Beta here is the propagation constant. K is the wave constant. So beta is the propagation constant. K is the wave number. Kc is called cutoff frequency, and we're gonna learn very shortly why it is called cutoff frequency. As I said before, like the perturbation technique, if we have losses in the dielectric, epsilon, instead of being like a scalar or like a real quantity, it will be a complex quantity with this format, which is epsilon r minus j epsilon r tan delta, which is the complex part of the dielectric constant. So far, those equations are general equation and can be applied for any waveguide. So what will the difference in waveguide will do? Different waveguides will like impose different boundary conditions. So those equations here are valid for like any waveguide, and what will make a difference from one waveguide to the other is the boundary conditions. So those are the general equations of the wave propagating inside a waveguide with the conditions that we said. We are just considering the positive Z component, and we are assuming perfect conductor. So those waves can be used to study the 3 different categories of wave propagating inside waveguides, which are transverse electromagnetic, transverse electric field or wave, and transverse magnetic wave, and we're gonna study the 3 of them in the next slides. So what is the meaning of TEM, transverse electromagnetic waves? It means that we have no longitudinal component. So Ez equals 0, Hz equals 0. So here Ez and Hz equal 0, and you might think that the solution for this case is the trivial solution, but no. If we look here, this solution, if Ez and Hz equal 0, this will equal 0, and we will have like a trivial solution, which is everything is 0, so there is no waves. This is true unless Kc also equals 0, which is unless K equal beta. So under certain conditions, this would be 0 over 0, and we can use other like boundary conditions to find the solutions that can exist in this case. So this like mathematical analysis in this case of transverse electromagnetic waves is a little bit complex. You can refer to the textbook to find it, but in conclusion, the transverse electromagnetic field is the same as the static field that can exist between the conductors. So for example, if we have like coaxial cable, and we have different potential at the inner conductor and outer conductor, there will be certain field structure. This same field structure is similar to the TEM wave. One thing we can learn from the analysis in the textbook is that TEM waves can exist only when we have two or more conductors. So like coaxial waveguide can carry TEM wave. But if the waveguide is a hollow, like a circular waveguide or rectangular waveguide, it can't carry transverse electromagnetic wave. So we must have two or more conductors in the waveguide in order to be able to carry transverse electromagnetic waves. Other than that, the waveguide can't hold transverse electromagnetic wave. Plane wave also is sort of like an example of transverse electromagnetic waves, and we had studied this in 304 when we talk about uniform plane wave. This is a kind of transverse electromagnetic waves. Okay, now we're going to introduce a number of terms or parameters of wave propagating inside a waveguide. The first parameter is wave impedance. So far, we talked about characteristic impedance, we talked about intrinsic impedance, and here we are talking about wave impedance. So whenever we have something on like sort of like a qualifier for the impedance, we know it is something different than the impedance that we consider in circuit theory. So wave impedance is defined as the ratio between the transverse electric and magnetic field. So Ex over Hy is the wave impedance for the wave impedance. In the case of TEM, we'll find that just substituting from the expression, we'll find that it is a constant that is the same value as the intrinsic impedance of the medium filling the dielectric filling the waveguide. So ZTEM, the wave impedance, is the same as the intrinsic impedance of the dielectric filling the waveguide. So it is E over H, Ex over Hy, or minus Ey over Hx. In more general, the transverse magnetic field equal 1 over the wave impedance, Z, the direction of propagation, like Az, this is the unit vector along Z, cross product with the transverse electric field. So it is the same, the wave impedance equals the characteristic impedance equals the wave impedance of plane wave in a lossless media. So we need just to emphasize here the difference between wave impedance and characteristic impedance of transmission line, because characteristic impedance relates the traveling voltage and current in like a transmission line, and it is a function of the line geometry as the material filling the line, while ZTEM, the wave impedance, it relates the transverse component of electric field and magnetic field, and we found it is only dependent on the dielectric material filling the waveguide. So there is a difference. The wave impedance is electric field divided by magnetic field. Characteristic impedance is voltage divided by current. The second type of, or second category of waves is the transverse electric waves. Transverse electric means the electric field does not have longitudinal component. Longitudinal component of electric field equals 0. The longitudinal component of magnetic field does not equal 0. So now we will have, like on the right hand side, here Ez equals 0, Hz exists. So we will have those four equations. Beta here equal K minus KC square. And very soon you will understand the meaning of, or like why the naming of Kc as the cutoff frequency. The propagation constant here will be a function of frequency and the geometry of the waveguide. So it's more complex wave structure than TEM. In TEM or in free space uniform plane wave, beta like is not that complex. So to find this solution, we know that Ez equals 0. All what we need to find the transverse components of magnetic and electric field is to find H of Z. So the equation for H and Z will be like this equation here. It's the homogeneous wave equation for H of Z. We know that H of Z does have this expression. It has dependency on X or Y, and the dependency in Z does have this value. Just substituting this dependency on Z here, the dependency on Z here, so K square will be like subtracted from it, beta square, and Kc will look here. This equation need to be solved based on the boundary condition of the waveguide. So it depends on the geometry. The wave impedance would have the same definition, transverse electric field divided by transverse magnetic field, and in this case we'll find the expression. It is frequency dependent, not similar to the TM wave, which was equal to the intrinsic impedance of the dielectric material filling the waveguide. The transverse electric wave can be supported inside closed conductor as well as between two or more conductors. So like hollow waveguides, like rectangular waveguide and circular waveguide, can hold transverse electric waves. Some people would call it a less common name, which is H waves. The third category is the transverse magnetic waves. Transverse magnetic means no longitudinal component for magnetic field, Hz equals 0, but we have longitudinal component for electric field. So we go back again to slide 8. We put Z equals 0, Ez is not. So transverse magnetic waves would have like the Maxwell's equation reduced to those four, And same thing here, beta, the propagation constant, equal k square minus kc square, and the wave equation, homogeneous wave equation that we need to solve for Ez, so that we can find the expressions for the transverse components. Here we just substitute the dependency on Z into the homogeneous wave equation. We find the expression for Ez, and the detailed solution would depend on the boundary condition of the waveguide. Based on the structure and filling material, we can find the solution. The wave impedance does have the same definition: transverse electric field divided by transverse magnetic field. Again, transverse magnetic waves can be supported inside a closed conductor like circular or rectangular waveguide, as well as between two or more conductors like the case of coaxial waveguide. Another not that common name for the TM, transverse magnetic waves, is the E waves. Now we are to discuss the attenuation due to dielectric loss. If we have losses in dielectric and losses in conductor, we would express them separately, alpha D for dielectric loss, alpha C for conductor loss, and the total attenuation constant alpha would be the sum of the two. Alpha C depends on the field distribution inside the waveguide and must be evaluated separately for each type of waveguide. From one waveguide to the other, we need to calculate alpha C, and we'll have one homework problem on this. For alpha D, we don't need to study the wave structure inside the dielectric. The attenuation constant of the dielectric can be calculated from the propagation constant and apply to any waveguide or transmission line that's filled with homogeneous dielectric filling. So the propagation constant in this case will be complex, and it would equal alpha D plus J beta. So this is, we are just ignoring the alpha C for now. If we put the expression for K, which is omega mu epsilon, in this case epsilon is for a lossy material is having this expression here, and tan delta, which is the loss tangent for most of the dielectric material used in this case, is much less than unity, and we can just use Taylor expansion here to solve for the problem. We just substitute here, we'll have the expression like this, and applying Taylor's expansion, we'll find gamma, the propagation constant, does have this value. Just substituting kc square minus k square as j beta, we'll find that gamma, the propagation constant, equal the phase constant multiplied by j plus the attenuation constant. This attenuation constant is just due the dielectric loss. Now we're gonna study the first type of waveguide, which is a parallel plate waveguide. This parallel plate waveguide is the simplest waveguide. It can support the three categories of waves: transverse magnetic, transverse electric, and transverse electromagnetic as well. To simplify the solution, we'll assume that the width is much wider than the height or the separation between the two conductors, and in this case we are neglecting all the fringing effect. So if this one does have V naught and this has 0, there will be some electric fields going from the conductor to the other, similar to the electric field in the capacitor. And we have like fringing effect. If width is much larger than D, the amount of fringing effect would be negligible with respect to the like uniform field, and we can just ignore them. The material permittivity and permeability is assumed to be epsilon and mu, and it fills the whole region between the two conductors. So like in this case we have two conductors, so this structure can carry transverse electromagnetic waves. So mathematically, the solution for TEM mode can be obtained by solving Laplace equation for electrostatic potential, because we said that the TEM wave structure is very similar, or it's similar to the wave structure in the case of a static field. So the solution would be the electric field is in the y direction. So we put on the top side we have V naught, on the bottom side we have 0. So on the top side, let me do this. So we have the electric field going from V to 0 like this. So very similar to the case of a capacitor, so on and so forth. And we have also here some fringing effect that we said that we're going to neglect, because we're assuming the width is much larger than the separation between the two conductors. Okay, so the electric field would be in the negative y direction, and of course the magnetic field would be perpendicular to it. Just erase this. Okay. So the electric field would be like constant along y direction. H would be constant along x direction, and we are considering a positive a wave propagating in the positive direction. K equal omega mu epsilon. Eta, which is the intrinsic impedance, equal square root of mu over epsilon. Like the voltage between the two conductors is the integration from 0 to d of minus E dot dl. dl would be in the y direction, dy. So we have this expression for the voltage. For the current, we can just like apply Ampere's law, or like we integrate the surface current along the top conductor, for example. So Js equal minus y, which is the normal to the upper conductor, cross the magnetic field. So this is from the boundary condition of electromagnetic waves along the z direction, and we integrate across the whole width of the conductor. We get the expression for the current on like one of the conductors. If we are to calculate the characteristic impedance, it would be V over I, and we'll find its expression. It is constant only depending on the geometry of the material, because this is now very similar to what we studied in transmission line. So transmission line between two parallel plates, or wave propagating in the TEM mode between two parallel plates, or does have the same structure of waves. So that's why like the Z wave impedance and characteristic impedance does have the same expression and value here. The phase velocity is also a constant, which equal 1 over square root of mu epsilon, which is the speed of light in the media filling between the two conductors. Now we move to the second category of waves that can propagate between, like in a waveguide, but parallel plate waveguide, which is TM. For TM, transverse magnetic, the magnetic field is transverse, does have no longitudinal component, but the electric field does have a longitudinal component. Because of symmetry, partial x equals 0. So if we go for our 4 equations here, partial x will equal 0, so there is no hy, and partial x, and there is no ex. We just have ey and hx. We'll find this case here. We have hx and we have ey. Hy ex will equal 0 because it depends on derivative with respect to x, and we have symmetry along the x-axis, and substituting into the homogeneous wave equation in this case, we'll find that the solution here depends on z. The solution for z is depending on Kc, and that's why Kc is called the cutoff frequency, which is happening when the wave number equal the phase constant. The solution for this equation, as we studied in 304 electromagnetic waves, is either a sine or cosine with two different constants. The constant must be defined or found from the boundary condition. The first boundary condition that electric field along the z-axis equals 0 because it's tangential to a perfect conductor. Ez equals 0 at y equals 0 and y equal d. So the tangential component on this conductor and this conductor, because they are perfect, equals 0. So Ez at y equals 0, Ez at y equal d, those equal 0. So this is a boundary condition. This boundary condition will cause will cause b to equal 0, and the other thing is that Kc multiplied by d equal n by, where n is an integer, 0, 1, 2, 3, so on and so forth. So beta will equal k square minus kc square. Just substituting here, we'll have beta equal k square, which is the wave number, minus n pi over d square. Ez will have this expression, an sine kc y, y multiplied by e to the minus j beta z. This is the propagation constant in the positive z direction. So this is the general expression for Ez, and it can have many different structure based on the value n. This n defines modes. So for n equals 0, it's called Tm0 mode. For n equal 1, it's called Tm1 mode. For any general n, it's called Tmn mode. So the solution, this is the solution for z. From the solution for z, we can find the solution for h, x, and ey. As we said before, ex and hy equal 0. When n equals 0, Ez will equal 0, and we are back to the TEM mode. For n other than 0, each value of n corresponds to a different transverse magnetic mode that's called TMN. For that mode, the phase constant does have this expression: if k, the wave number, is greater than the cutoff frequency, beta will be real and we have propagation. If k is less than kc, beta will be imaginary and we have non-propagating mode. The mode will be decaying very fast, and that's why we call this cutoff frequency, and this is the expression for the cutoff frequency. So in this case, the waveguide is acting as a high-pass filter. It can propagate waves above certain frequency. Waves below that certain frequency, the cutoff frequency, will be decaying mode. When beta is pure imaginary, this is a rapidly decaying waves that's called like cutoff modes or evanescent modes. Waveguide mode propagation is analogous to high pass filter, as we said. The wave impedance equal the tangential electric field divided by the tangential magnetic field, which have the expression of beta over omega epsilon, which is a function of frequency. One important thing to notice here that the wave impedance is pure real when f is greater than fc, but if frequency is less than the cutoff frequency, beta will be pure imaginary, and consequently the wave impedance also will be pure imaginary. The phase velocity is also a function of frequency, and it's equal omega over beta, and it is greater than the speed of light in the medium. So this is the phase velocity, because like this is confusing many people. How come we have something greater than the speed of light? What is greater than the speed of light is the phase velocity, because the wave, you can see that the wave is propagating like between the two plates this way. So if this is the z direction, it's as if we have wave propagating like this. So the wave travel longer distance along its direction of propagation than z. When we calculate the phase velocity along, okay, where is the marker? Sorry about that. Okay. So, like along this line, the wave traveled longer distance, so the phase here is larger than the phase if the wave is propagating directly in a straight line. So that's why the phase like velocity is larger than the speed of light, but the power, the speed of propagation of power, which is the real quantities that propagate, will always remain bounded by the speed of light. So don't be confused, it's called the speed, like phase velocity, but it is the velocity of the phase variation, not the velocity of propagation of anything, because here this is the direction of propagation, and because the phase travel like, or the signal travel as if it is traveling like longer distance, you can see the phase velocity is larger than the speed of light, but the signal itself or the power carried by the signal will never travel larger with the speed larger than the speed of light. So the guide wavelength lambda g equal 2 pi over lambda, which is the distance between equiphase planes along the z-axis. we know that lambda g is larger than lambda. Lambda equal 2 pi over k. So the phase velocity and guide wavelength is defined only for propagating modes. For non-propagating modes, beta is imaginary, and those two quantity has no meaning. Lambda g and VB, speed of like phase velocity, doesn't have meaning for evanescent modes or non-propagating modes. The third type, or sorry, we are not yet. Okay, now we need to study the power propagation for the case of transverse magnetic waves. Power propagation is studied by the Poynting vector. So writing the point vector for any waves, it's E cross H, like propagating across the cross section of the waveguide, taking the real of that. This is the power, and if we average this over one period, so it would be the average power passing through the waveguide. For n equals 0, it will have certain expressions. This is transverse electromagnetic waves. For like TM modes, n greater than 0, it will have a different expression. So B is positive and non-zero when beta is real. If beta is imaginary for evanescent modes or non-propagating mode, it will B will equal 0 because it depends on the real value of beta. Okay, now coming to the concept of calculating the attenuation constant because of the conductor. So how would we do this? We can use like this method, alpha conductor equal power loss divided by 2 B naught. How to find power loss? So we just found power loss B naught, which is the power flow down the guide in the absence of losses. BL is the power dissipated per unit length in the two lossy conductors. So we need to find the surface current on the two conductors and the surface resistance and calculate the total power dissipated on the surface resistance. This will give us the conductor power loss. If we have the conductor power loss and we have the power flow, and because it is AC, we have like 1/2. So the conductor losses will equal this expression. So in this case, if we are to like calculate RS and substitute to find BL, substitute back here in this expression, we'll find that alpha C equal like this expression. You can like review the derivation in the book, and also we'll have one problem in the homework to do like similar analysis. The third category of waves that can be carried on waveguide is the transverse electric waves, which has no longitudinal component for E, but it has a longitudinal component for for H. In a similar way, due to symmetry, partial X equals 0, and we can find the homogeneous wave equation for Z. The homogeneous wave equation solution is like bounded or like sort of like controlled by the boundary condition. So writing the general solution for H of Z, we'll have this expression. The boundary conditions that we have is that EX equals 0 when Y equals 0 and Y equal D. So there is EZ is already 0. So the other tangential component in this case is EX, and we need EX to equal 0 at the two conductors. Substituting those boundary conditions here will give us EX with this expression. The boundary condition would make A equals 0. So the boundary condition would require A to equal 0 and Kc multiplied by dt equal n by n can be any number 0 or any positive number. According to this, A will equal 0, B will be like Bn, n is the mode number, and we will have this expression Ey and Hx are always 0. If n equals 0, Hz will equal constant, but Ex and Hy will equal 0, so there will be no no TE 0 mode. The propagation constant will have this expression, and it is the same as Tmn. The wave impedance would have this expression. Z, the wave impedance, is pure real above the cutoff frequency and pure imaginary below the cutoff frequency. The phase velocity does have the same expression. And important thing here, there is nothing called TE0, because if n equals 0, E and H will equal 0, and the power flow will equal 0, so there is no existence of TE0 mode, while TM0 mode is identical to the TEM wave. The power flow, in a similar way to what we just discussed for transverse magnetic waves, does have this expression, and in this case we'll have, like the case of two parallel waveguides, two parallel plate waveguide would have this expression. Again, B is positive and non-zero if beta is real, B equals 0 if beta is imaginary for non-propagating waves. The attenuation because of the conductor can be calculated in a similar way, and in this case it will have the case of two parallel plates waveguide, it will have this expression. And here, this is a summary of the things that we had learned so far in this lecture. Thanks everybody, and meet you in the discussion session.